Okay, so we can start the last session of today. And now we have Javier Matulich talking about superrotations at space like infinity. So there are a few people entering again. So then.
Really? Can we just? It's really a stupid thing.
Is that one?
No, it's another one.
It's the old one.
Yes.
I uploaded 5 minutes ago.
Can we
So,
modify it rap quickly or let's just? No, it's just don't worry. It's really not important. Don't because I had a last time modification, but it's something that
here.
but it's okay.
Okay, sorry.
It's perfect. No, don't worry.
Okay, so well, please, Javier.
Hello. Yeah. Hello, everybody. Can you hear me? Yes. So, well, I would like to thank the organizer for giving me the opportunity to give this talk today. Well, I'm going to talk about a work in collaboration with two good friends, Adrian Frederici and Román Rossiconi, that are present here, I guess. Román, is Román here? Ah, you are here. You are usually there in the shadows. And well, this is going to talk. I'm going to talk about a canonical realization. No, it's not the canonical, but a canonical realization of these superrotations at the spatial infinity. I hope everything will be clarified, and I hope everything will be clear, and you will understand what's the reason, because it's important to solve this problem. Well, we're going to get there at some point. So let's get started. I just want to start with a brief introduction. It's going to be, well, I'm going to start with some, the realization of the symmetry in the BMS4, the one that was done by the BMS people in the 60s, when you approach null infinity. So I'm going to define BMS4 in a very brief way. I'm pretty sure that everybody here knows what's BMS4. So I'm not going to spend much time on that. After that, I will comment that there is actually a bigger extension, a bigger group that is known as superrotations. I will present briefly the both version, and I have to comment right now that we are going to canonically realize, so we are going to be closer to a canonical realization of one of them, the one of Campiglia and Lada, in which you have the full diffeomorphism on the two spheres, not the one of the Virasoro symmetry, the one that was proposed by Glenn. I hope we will be able to find that in the future, but this is what I'm going to talk about today. And for that, I have to comment that we are going to follow the Hamiltonian approach, the canonical approach. The approach is really powerful, as you probably all know. But what is interesting on this problem is that actually we had to mix the tools from two different topics, the one of the Hamiltonian approach and the one of the phase space formalism, in order to cure some problems. So I'm going to relax the asymptotic conditions of Marc and Cedric, Marc Henault and Cedric Trossard, the one that are invariant under VMS4, in order to accommodate this bigger symmetry. Unfortunately, or fortunately, I don't know, this relaxation gives us many difficulties, divergences and non-integrabilities in the charges. And we had to mix both, the best of both topics, in order to solve that problem. That's a new stuff. That's a novelty of this work. And in order to do that, I would like to first show the canonical realization of VMS4 that was provided by Marc Henault and Cedric Trossard like 6 or 7 years ago. And for that, I have to introduce the Hamiltonian. I have to present very briefly the EDM decomposition, the Hamiltonian gravity in its Hamiltonian form. And I will show how these asymptotic conditions were generalized by Marc and Cedric in order to accommodate VMS4. And then I will go directly to superrotations, and you will see precisely what is the relaxation of those asymptotic conditions in order to accommodate superrotations. As I mentioned, this is going to complicate everything, and I will show you how we deal with that. This is a canonical realization. There could be another one. Well, that's something that we can explore in the future. But this is the one that we have found, and there is some interesting structure that I would like to show now. Okay, let's get started. A brief introduction. So we'll know that there is a solution, the solution space of four-dimensional asymptotically flat metrics written in this way in bounded coordinates. This is an R expansion where we are expanding around the Minkowski metric in bounded coordinates. And we know that there are some free functions that are arbitrary functions on U and XA on the advanced or retarded time and the coordinates on the sphere. And you have some freedom, some free functions that are related to the bonding mass, the angular momentum aspect, and some bonding mu's that are the ones that encode the gravitational waves. So you can ask now, under which symmetry these asymptotic conditions are invariant, okay? The naive, I don't know, I thought about that. So what do we expect? To have the isometries of the Minkowski spacetime, just Poincaré. But this was shown in the 60s that this is actually not the case, because these asymptotic conditions that I presented in the previous slide are actually invariant under an infinite dimensional extension of Poincaré that is well known as the VMS group. It's quite easy to check actually that this is the vector that preserves those asymptotic conditions. And the most interesting part is that actually you have some component in which you have an arbitrary functions on the angles, okay? That are precisely the super translations. And if you can think in the super translation as they are acting by shifting the retarded time by a different amount at each point on the sphere. Okay, this is what how this super translation acts. But as I mentioned, and well, it's related to what I'm going to show today. There is a even bigger extension of the Poincaré group, which is known as superrotations. In this case, there are two proposals, at least two proposals. There might be some other nowadays, but there are two proposals. The one by Barnich and Trossard, in which you have an extension that is given by Virasoro, Cruz Virasoro, direct product with the super translations. And the one that is going to be more relevant, in our case, in the case I'm going to present today, is the one by Campiglia and Lada, in which you have the full diffeomorphisms on the two-sphere, direct product with the super translations. Just a comment that there is an extra citation here that is related to the fact that they were doing some extra analysis in this regard, and this is precisely what is actually relevant for what I'm going to tell. What I'm going to tell. Unfortunately, and this is I want to stress on this point that the superrotation has been elusive in spatial infinity settings. Okay. What happened at spatial infinity? We know that this was puzzling because from the work of Regé Teltenbaum from the 70s, they were not actually able to find any VMS, any super translations. They proposed some boundary conditions. I will show those in a minute. And what they found that the asymptotic conditions are invariant under Poincaré and nothing else. This was puzzling because actually the VMS symmetry is a symmetry of the action. So the action is left invariant under this symmetry up to boundary terms. Okay, so especially in the case of Hamiltonian formalism, so it was no sense to do not have this symmetry in slices adapted to spatial infinity when you approach spatial infinity. So it has to be there. But the problem was solved some time ago, 6 or 7 years ago, by Marc Henault and Cédric Trossard. What they did was to propose some twisted parity condition. I'm going to show explicitly what that means. And they were able to accommodate or to propose some boundary conditions that are actually invariant under the VMS4 symmetry. Some work has been done since then. Well, I'm going to comment on some of my work in particular, or some work on the collaboration. We were able to find the asymptotic condition for n equals 1 supergravity. So we canonically realize a super VMS symmetry, super VMS algebra. We also, well, I changed my talk 2 days ago. I'm not going to comment on the reason, is meaningless. But my original idea was to talk about 5-dimensional gravity, and so VMS5 symmetry. And so that's also an interesting problem. If there is someone interested in that, I will be happy to discuss that. The canonical realization of VMS5, which is something completely new. There were no any VMS5 before our work. And there is also, well, I'm pretty sure that now it's quite common to hear about the logarithmic supertranslations, and this is a paper in which these authors canonically realize this symmetry. This has become very important for many reasons, but I'm not going to discuss on that. Okay, so the question, and I went too fast, but well, it's already there. In every single, it was quite common to have this question: where are superrotations? In every spatial infinity analysis that in every conference. And so the question was, where are superrotations? The answer was, we don't know. So we thought that this was an important problem. For some reason, everybody was interested in that. We know that superrotations are important, are really important in all this story. So the question was, where are superrotations? So we say, well, someone has to solve this problem. And we tried, and it was very difficult. But what I'm going to show today is one realization of that symmetry, a la Hamiltonian. Okay. As I commented, there could be some others, but this is the one that we are proposing, and well, it closes quite nice, and with some extra structure, unexpected structure that is also quite nice. So let's get started, because I'm probably super late. I'm going to follow the Hamiltonian formalism, the canonical approach. For that, I have to consider an affiliation in particular. I have to follow the ADM formalism. That means that I'm going to foliate the spacetime in a very precise way. This foliation induces a certain form of the metric that is given by this expression here. So you have an induced metric on this hypersurface, a lapse and a shift. Okay? This is a complete set of functions that are equivalent to the metric, the G mu, the metric on the spacetime. This foliation and following the ADM formalism, or if you want the Hamiltonian formalism, allow us to write the Einstein equation in its Hamiltonian form. What we have here is the spatial metric, its conjugate momentum, some lapse and shift that are there, that are Lagrange multiplier that enforce the constraint to be held, and a couple of constraints, well, many of them, but which are the Hamiltonian and momentum constraint. Here I have to stop and comment on this boundary term, which are really, really important, are actually the most important piece in the Hamiltonian action, which is this boundary term. This boundary term, this surface integral, is there in order to have a well-defined variational principle. It's really important. It's actually the origin of the charges, the origin of the Hamiltonian charges. It was proposed by Regé-Telgenboim the following follow-up conditions. That is something natural because you have to deal with this boundary term. So you really need to say something about the fields and how they decay. They propose this boundary condition when you approach spatial infinity, which are the ones that are that we are going to deal with today, and using the Hamiltonian formalism. But in this case, for those boundary conditions, there was a problem with some logarithmic divergence in the kinetic term. So the PQ dot term is actually has a logarithmic divergence. And this problem was solved by Regé-Telgenboim by imposing some parity condition under antipodal map. And the problem is that this particular condition, for this precise case, there is no room for VMS4. So the solution was, we have the result that they got was Poincaré and nothing else, just that. So some time ago, like 6 years ago, Marc Hinot and Cédric Tossard, you can see here the reference if you want, if you are interested. They proposed some twisted parity condition in which you have two pieces. One piece has a definite parity, like here for the metric, even parity. And there is another piece with the opposite parity. But this extra piece goes precisely as a linearized diffeomorphism, as a gauge transformation, okay? There is a good reason for that. In practice, this takes some extra derivatives that you can use to integrate by parts and form the constraint. So you remove some of the issues that you can find by allowing this kind of stuff, by adding some derivatives, you integrate by parts, and you remove some stuff, some issues in the theory. What is also interesting on that is that this actually accommodates Tabnat solution that was not accommodated before. But as I mentioned, this complicates the charges. The charges are not integrable in principle, and there are also some divergences. Okay? But Marc and Cédric shown in this paper that actually all these issues, all this problem with the theory, with the canonical realization of the symmetry, can be cured by just imposing some order. So they're imposing the constraint to hold the asymptotic constraint to hold up to from order R to the -5, and also the non-integrability and the Bush charge was solved by removing the leading term in the expansion of the GRA component. Okay, that's so there is no. It was difficult to solve the problem, but the usual tools were enough to integrate the charge and to canonically realize the BMS4 algebra. And here is the most important thing here is that actually the boundary conditions that they propose are invariant under these symmetries. This is the asymptotic expansion of the chi and chi-A, which are the expansion of the generators of this symmetry, of the parameters of this symmetry. I'm not going to say more on this because I do not have time. But here what we have is are the boost, the spatial rotations that are now not arbitrary, of course. They are, you have to solve the Killing equations. But what is interesting on this analysis is that actually you have T and W, which are related to translations. And in this case, what they had found is that T and W are now arbitrary functions on the angles. So only the zero modes of T and W corresponds to the translation, time-like translation and spatial translations. Okay, so now you have an arbitrary function that you can expand, and that's the way that VMS appears, and super translation appears through this T and W. You can follow the canonical approach. You can integrate the charge, as I already mentioned, and this is going to be the generator of the symmetry that now is finite, integrable, and canonical. Okay, so no any issues on this in this regard. It's not going to be the case of super rotations. And then you can compute the Poisson bracket of those generators, and this is the result. It's not obvious that this is actually the BMS4 algebra, but it's written in a unfamiliar parametrization. It was proven by Mark and Cedric that actually this is BMS4 by performing this the analysis in which was quite similar to what Hernan Gonzalez did this morning. You have to provide some different gauge, and you make the connection between spatial infinity and null infinity. Okay, and what is important here is that actually you have two functions, W and T, in which the odd part of W and the even part of T are actually combine in a very precise way, such that this makes sense to the unique. You remember that there is only one function that parameterizes super translations at spatial infinity, at null infinity. Okay, let's go to super rotations. So everything's clear now. This is we are going to follow precisely the same procedure, the canonical approach. Super rotations. Well, here you have the reference of this paper, which has a bit more than 1 year. So what we're going to do is to propose some extension, some relaxation of the asymptotic conditions that were proposed by Mark and Cedric in order to have something, in order to accommodate these super rotations, or something that we think that is these super rotations. What was really important in this analysis is something that was actually done at null infinity, in which you have something that is asymptotically locally Minkowski. This implies that the metric at the boundary is not fixed. Okay, it's a standard thing that you do at null infinity. So what is our goal? Our goal is, at least for this realization, is to have B, which was the boost, and the rotation, the Lorentz rotation, to be now arbitrary functions on the angles. That's our goal, at least for this regard. So let's try to find some boundary conditions, some asymptotic conditions that allow us to do that. The main difference here is this GAV, which is now not the metric on the two-sphere, but some arbitrary function on the angles, GAV. So it's not constant anymore. This asks for some extra terms, some relaxation on the momentum conjugate, pi RR and PAV. And what is interesting on this asymptotic condition, they're actually invariant under the symmetry that we are looking for. The diffeomorphism on the two-sphere, the direct product with the super translations. Okay, so we have proposed some boundary conditions, some asymptotic conditions. They are invariant under the symmetry. Now we want to canonically realize that symmetry. That's a tricky part of the computation. So In order to do that, we are going to follow the symplectic, procedure. So we are going to consider, as this is very well known for gravity, that this is the symplectic extractor for gravity. If you use use the asymptotic condition that I just proposed, we can see that there is actually an R and logarithm divergence in that the symplectic extractor, if you want, in the kinetic term in the action, the Hamiltonian action. And this is the point in which we mix both methods, both procedures. So these divergences, because of the freedom that we have in the formalism, we were able to cure that, to remove that by adding an extra surface term that is given precisely by this expression here. So we remove that, and what we do with this is to remove all the divergences in the charges. So we renormalize the action by adding a boundary term, and what we get is a finite charge. But the problem is that the charge remains non-integrable. And now let's try to integrate that charge. And for that, we follow the canonical approach that I have already discussed in the previous case. And here we can see that this is so we use the asymptotic conditions for every field and for the parameters. And this is the result. This is a non-integrable piece. You can see here that this is not integrable. We cannot put the delta outside. There are 4 of them, but they have different resolutions. So the first 2 can be integrated by considering some field-dependent redefinition of the parameters. So which is given by this. The method allows us to do this. So what we are actually doing is to set T and epsilon tilde to have precisely this form, and now we demand T and epsilon to be field independent. Okay, that's precisely the. Please.
Thank you. In the superrotation at Sky, I think the usual condition is to impose that the determinant of the celestial sphere is fixed, but you allow for the other part. Here, if I follow your notation, you still allow also for the volume of the celestial sphere to vary.
Exactly.
So do you get something, why you didn't fix square root of G? Because you could, or because you just, why you were like not fixing that part?
Yeah, that was an option. We followed that path, I remember, but there was some abstraction. I cannot remember now. But we can discuss later. But it's true that this was an obvious selection. You know, it's something that in null infinity you do. Yes. No. Well, what it's going to do is to actually remove some of these stuff. You know, every time that you have G, no, well, this one, yes, this is precisely the yes. But the problem there was something that was not working. But we can discuss later.
And just to double check, when you demand that, for instance, T is now field independent, another way of saying that is you actually are requiring F to be field dependent. Is that right? Because you want the contributions from F, the variation of it on phase space, to cancel those coming from the second term.
Yes.
Okay.
So, yes, so with this, we can remove, or we can integrate the first 2 lines in this non-integrable charge. But as I mentioned, the obstruction only now involves only the variation of the boundary structure, right? As I said here, so PAB and GAB. Okay, so as I said, well, this is everything that is left. These 2 pieces that are not that easy to solve. Okay, let's continue. So this is our proposal, and well, in the title there's some boundary graviton in it, and I hope in the next slides that will be clarified. So the way that we managed to integrate that chart was by adding, by considering a couple of extra boundary fields, CAB and FAB, and we were able to fix this problem by considering some boundary modification in the boundary symplectic extractor. Okay, let's go like that. And then we demand these new fields, the CAB and FAB, to transform in a very precise way, okay? Such that we can remove these non-integrabilities. Okay, this is the only thing that we do by hand. But I have to say that this is exactly the same that was done by Mark and Cedric in the case of electromagnetism, just to be sure that this is not a crazy thing, but something standard in our standards. So we demand the new fields to transform precisely like that. That allows us to remove the non-integrable piece. But this is actually not enough because, as you can see here, this is mixing the new field with the field that we already had in the. There's some question. There's some.
Can I ask, what's preventing you from doing exactly the same thing you did for the first two terms as the last two?
There is no. Well, the main reason is because, so this was quite obvious because you can see here that, like in a very precise way, there is no any indices here. That was very, very easy to check. So what I want to say is that actually, what allows you to do that is that actually there is a solution for this equation, which is epsilon equals to that, But that is not the case here, for instance.
I see.
You see?
Right.
Because the indices structure makes the difference, if you want. It's more complicated than that, but this is one of the answers.
Is the field C and F has anything to do with the NVAC, like the fact that when you want to define something that transform, you add some vacuum structure, like the goldstone or something that transform in a specific way such that you recover some covariance? Or this, I mean, do you have a physical interpretation of what are these C and F?
Yes, I'm going to provide it
Okay,
now.
thank you.
Yes. Okay, so, but as I say, there is some, this symplectic structure, this modification in the symplectic structure. There is another question. The symplectic structure involves not only the new fields, but also the field that we already had in the phase space. That means that when you are, because what you have to do is to ask the symplectic structure to be invariant, not the symmetry. And this is true only if you modify the transformation laws, but we also add a couple of extra pieces here. And what I can say now, because I want to make sense with this boundary graviton, is that actually these transformations are precisely the one of linearized gravity in a curved background. Okay, that's the reason because I'm saying boundary graviton here. Let me be much more precise here, is that actually I can go here, yes. This modification and the introduction of these two fields allow us to integrate the charge, and the charge actually gets a couple of extra pieces that are precisely this. So the charge now is the previous one that we have already integrated, plus these extra pieces. And these extra pieces are precisely the momentum, the Hamiltonian momentum constraint of linearized gravity in 3 dimensions, 2+1 gravity in 3 dimensions. Let me remind you that actually every field here depends on time, okay? So this looks like a 2-dimensional thing, but it's actually 3-dimensional because time is always there. But we are performing all computation in a fixed time, so that's the reason. It's a Hamiltonian formalism. So this is telling us that, well, these guys are transforming as a linearized graviton. These are precisely the constraint of gravity in 3 dimensions, of a linearized gravity, of the Hamiltonian action of Pauli fields, if you want. So let's try to make that sense. For that, I'm going to linearize gravity, 3-dimensional gravity, and I'm going to put some alpha here. And what I can say is that actually, you see here, these 2 pieces are precisely the one that we have used to modify the symplectic structure. That was like a F G dot plus P C dot, okay? Plus a couple of extra terms, which are precisely the one that appear in the charge, okay? So what I'm saying that this is actually the alpha part when you collect on this parameter that I'm using to expand. This is precisely the action that you get from linearized gravity, from the Pauli fields action in its Hamiltonian form. Okay, and this is the form of the constraints. It's highly non-trivial. There are many derivatives that complicates everything, especially in the closure of the algebra and Jacobi. But let's go there. And another comment here is that actually there is a lambda here, but this lambda takes a very precise value, 1/2. So this is a background. The background is not fixed. But it also has a very precise value, a positive cosmological constant. And this makes sense with the analysis that you can make at null infinity. So it's something that you expect to have. This is the final form of the integrated charge. I think I have like 1 minute. There is the part that was already integrated by modifying the symplectic structure, and this is the extra piece that goes precisely as the Hamiltonians of this linearized gravity action, the graviton. But now you have the super translations, and now, as I said, YA and B are now arbitrary functions on the angles. And this is the one that are going to make sense to this diffeomorphism, this diffeomorphisms on the two sphere. Okay, and it's also I also have to comment that there are some subleading symmetries. Okay, that appear there. It can be killed, but by selecting, for instance, that the square root of G is removed, but there are some issues on that, as this is related to Celine's question. This is the final form of the generator, and now let me just take a couple of minutes just to show that actually the Poisson bracket of the generator closes in a nonlinear way. You have a nonlinear term here, so this is a quadratic in the fields, 0. Now B and YA are arbitrary functions, so this is our realization of these superrotations. We have some extra symmetries, subleading symmetries that we are still trying to understand. This is now Lie algebroid because we have everywhere we have G, which is now an arbitrary function. So we do not have an algebra, but an Lie algebroid. No, Lie algebra. We check Jacobi, which was the most difficult part of the computation. And well, some comment and remark. Well, I think I can stop now because it's already 0. But... Okay, thank you.
Or other questions?
Can you show again the previous slide? One more, where you had the charge algebra.
Charge algebra. This one.
Right, so my understanding is that every time you have these field-dependent cocycles, you have some problems with covariance. Like your background structures are still present, so your construction is not general covariant. Is this something that you can comment on in this case? Like, I'm more familiar with the case of Scry, not so much with the case here, but like, did you need to introduce some boundary fields that were not dynamical in your construction, and then maybe their presence is, at Scry, you would ask questions such as conformal invariance on your construction for the charges. And if you have a field-dependent cocycle, that typically fails. Do you have something similar here? Could it be a sign of that?
I actually, I don't know. No, this is the kind of thing that we still have to understand better. Yes. At least from my point of view, I don't know if Adriano can say something more about that. But yes, there is still some stuff to understand. And I think it's quite related to the fact that we need to connect our approach, our result with the null-infinity case. And that is still a work in progress. It's a very difficult computation. But that, I think, will clarify some of your questions.
Can you show me the charge that you get finally?
The charge.
Yeah.
This one.
So the thing that comes with W, does it have a definite parity?
You mean
The whole thing? Yeah.
Yeah, it has. Well, I didn't say anything about parity, but we are using. So we have selected some parity, but this was a definite parity. We are not precisely using some twisted because we wanted to keep the problem simple.
No,
but,
I mean.
No. You are talking about what is the parity of what's
right,
in the bracket.
the whole thing in the bracket.
Yes or no? Yeah. What I can say is that W and T are precisely the one of Mark and Cedric. That means that actually everything here has a definite parity. Yes. It's quite. Maybe I can understand what you are asking because there is some extra terms that are correction terms. And in the paper of Mark and Cedric, they have a definite parity, this combination. And the full combination actually has a definite parity. Not if you take only the two first, it's not true. So that this is something that tells us that this is the correct result. Is this clear what I mean? So the full thing has a definite parity. but not the first two terms. But well, we can talk later.
Other questions? No? Okay, don't see other questions, so let's thank Javier again.